Semiconductors, Mr. Aravind Prasad. May I invite Mr. Aravind Prasad onto the podium. 20 plus years of experience in again power electronics. I think he is expert in charging, power supplies, inverters. There's a whole list of things. I think he has worked in CPRI, Central Power Research Institute. Okay, that is one of the premier government's institution way back in power electronics.
Hello everybody, my name is Aravind here. We spoke about 1000 kilowatt hour, right? I will just scale down this by 100 times. I am going to talk about inverters in the range of 10 kilowatt, right? So coming from a semiconductor industry, right? I've been part of a lot of activities in the design for inverter for last two and a half decades, right? And I'll explain my exposure in the market, how semiconductors have been part of inverters, especially from the Indian perspective. And later on, I will touch how silicon carbide is actively participating in four-wheeler vehicles. Now, let me first talk about the powertrain architecture. So as you see here, the three important components, where is the highlighter? Okay, the three important components in a powertrain definitely is the transmission, which is either belt-driven or gear-driven or direct drive, wherein hub motors come into picture, right? And the second most important component of the powertrain definitely is the motor. We have BLDC motors. In the future, we will see a lot of SR motors, considering the challenges in rare earth magnet for magnets, right? And coming back to PMSM motor, we are also looking at internal permanent magnet motors are coming into picture where the algorithm is getting complicated. This is the second component, most important. But coming to our subject discussion today, the inverter, okay, which is the electronic part which drives the motor, looks into the feedbacks of the user, etc. So there are two different important segments in an inverter. One is the power control unit. Second thing is the vehicle control unit, right? Vehicle control unit predominantly comes from the four-wheeler market. As on today, no vehicles are using vehicle control as part of two-wheeler or three-wheeler in India as of now. So the important part of the power control unit is to just drive the motor based on field-oriented control or any algorithm that is available. Within that, the three important components, definitely the power management section, where all the power rails required to drive your MCU, which is at 3.3 volt, your gate drivers are IPMs at 15 volt, and all your sensors, which are at around 5 volt, etc., are done by the power management unit. The power stage is the power behind driving the motor, which I will discuss extensively in the coming slides. Then the digital part is all about the MCU, which is having the motor control algorithm based on FOC. Then the VCU, which is right now part of the PCU itself, does the major important interface to the outer world, to the user, right? It understands the throttle behavior of the user, the braking behavior of the user, and accordingly controls the speed, acceleration, etc., which needs to be done very effectively to make an electric vehicle reliable. So coming back to the battery side, so we always spoke about two-wheeler and three-wheeler are having 48 volt batteries, exactly to say 51.2 volts. There are also battery technologies on 60 volt, 72 volt. But one important thing is a lot of inverters are coming with an auxiliary power supply of 12 volt. So this is to add redundancy to the inverter. In case there are some issues with the main battery, your digital section should be still running with an auxiliary battery, right? That is the idea behind it. Now coming back to the approach of motor control, electric vehicle needs highest torque at the standstill condition, right? With a payload of around 135 to 150 kgs, right? What is the best approach to this market, right? Is it censored or is it censorless? I would definitely go with censored because we need to deliver full amount of torque at startup, right? What are the options available for us in order to determine the angular position, right? First thing is Hall, then we move on to encoder. Right now, most of the high-end vehicles are coming with resolver. And in order to optimize the cost, we will be moving to inductive position sensor in the future. These are the available options that we have. Now, having spoken about the architecture, what is the real expectation of an electric vehicle? Is it range or is it drivability? It's a combination of both, right? How do we identify the best balance of drive versus range is going to be the driving factor for the success of a EV inverter. So we can very easily increase the range of the battery by sizing the battery very big. But we hit a point where the weight of the battery can counter effect the mileage, right? At the same time, we can increase the durability of the vehicle very much by having a very powerful motor. But we hit standstill when it comes to designing a power inverter. So now the industry has come to some kind of a trade-off what we need to do, right? So if you talk about specifically the two-wheelers, right? The range, the kind of range expectation of the users can be attained in a power range of around 3 kilowatt to 3.5 kilowatt. I would rate around 3.3 kilowatt with a current capability of around 100 amps. But the biggest challenge when it comes to power engineers like us, everybody speaks the cost, the performance at 3.3 kilowatt, but they are saying that my vehicle should have a peak power of 2 times, right? 6.6 kilowatt at 200 amps. This is where the challenge really comes to us while designing a power inverter. So I will probably go through this transition, why people have gone through this in the coming slides. Now, what are the solutions that semiconductor companies like us can address in this market? It is just, I've added all the components that is feasible in the inverter section that you spoke about, power management or power stage or the digital section. The first thing is the core to the inverter is the MOSFETs, right? So we have technologies in terms of super junction MOSFETs, 100 volt, 120 volt, 150 volt. When it goes to four-wheelers, we have silicon carbide devices which address battery banks of around 800 volts, right? The next important thing is gate drivers which drive the MOSFET. Then the power management section addressing all the rails, be it a DC-DC converter, isolated converters, DC-DC, LDOs, and sometimes the protected IPD switches for protection. Then the other auxiliary ICs like op-amps, comparators, EEPROMs, etc. We also offer a lot of extensive devices around it, like transistors, diodes, shunts, right? We can also speak about other things. The other important component which is part of an inverter is definitely the MCU, the capacitors, and the sensors. So this is the core of it, right? But I would like to take this time to discuss the evolution of inverter in the last 2.5 decades, particularly focusing on the power stage. So what does the power stage have in the simplest form, right? We have MOSFETs, we have gate drivers, then we have capacitors and current sense for production. Now, the very initial stages of EV development started with cost as the primary requirement, right? Then we are in today's stage where cost is important, but performance is very important for the motor inverter EV to catch up in the market. So in the future, as the number of vehicles are absorbed in the market, reliability will be very, very crucial, right? Right now, we are seeing only batteries burning in the market. Very soon, as the numbers increase, the inverters will start failing in the market. So how do you make it reliable is very important. And finally, how do we optimize the cost when everything is met is the focus. Now, starting from around 2.5 decades, we started with 250 watt e-cycles, e-bikes coming from China, right? Then, since of the inclination or the kind of payload that we use in India, we started increasing the power to 500 watt, 1,500 watt. Now we are standing in the range of 3 to 3.5 kilowatt. So as you see, as on today, most of the acceptance of the vehicle is mostly predominantly by service companies or urban users, right? So they have a short distance travel, they have a defined payload. But the moment the acceptance of the vehicle goes to suburban or rural, the vehicles will be exploited for range, they will be exploited for load, right? That is when we make sure that the amount of inverters going into the market, we make it reliable. And one thing that will come for the future will be 10 kilowatt peak power requirement for two-wheelers. That is what we think. Now coming back, how the technology has panned out on the MOSFET side, right? So initially, the design being cost constrained, right? We went with TO220 package, paralleling a lot of MOSFETs. So over the period of time, as you see, whenever the inverter fails, do tin MOSFETs extra daldo. So that has been the trend, right? And even today, the way people are talking about the inverter is kitna MOSFETs laga hai andar. Okay. So this is not the analogy that we would like to talk. See, what we would like to understand is what is the power required, what is the type of MOSFETs, and what is the number of MOSFETs we need, right? That analogy needs to come into the power electronics design. Now, going forward, as of now, we are the most popular device in the market is based on a package called toll, right? So there are designs based on 3 devices in parallel, 4 devices in parallel, or 5 devices in parallel. This is the trend. As you see, a lot of MOSFETs being integrated. But looking at the reliability perspective, right, we have a lot of challenges when we are paralleling more MOSFETs. So there should be a trend where we need to have modules coming for EV inverter. That is the second phase. That's the final phase of the design, right? One more thing is when you do modules, you can bring a lot of reliability test at a module level than doing at the PCBA level. That is going to bring the reliability at the power stage at the MOSFET thing is what we foresee. The second thing is the PCBA, right? The PCB, we started with a very, very poor quality FR4 PCBs, which are very cheap but very, very bad, right? When the board started failing, we started adding copper strips to the traces to drive the current, right? Now, predominantly, everybody is using metal clad PCBs, but we do have a lot of challenges in metal clad from the manufacturing perspective. The repeatability is a problem, right? The accuracy is a problem, right? How do we address this? The only way forward is having a module and having a bus bar approach. This is typically used in most of the vehicles, the popular vehicles already, right? The other advantages this brings in is you reduce a lot of parasitic inductance effect in the vehicle or in the inverter, right? The third part, the gate driver, right? So gate driver is something ignored pretty much, but this is going to be one of the mainstay from the reliability perspective, right? We have been using discretes, the totem pole circuits, then we went to non-isolated bootstrap. Now we are considering isolated not per se for the isolation perspective, but the bootstrap has a limitation that if you want to run the vehicle beyond 90% duty cycle, it has a limitation, right? So if you go to isolated, you can go beyond 90%. There are certain advantages at the vehicle level that can be addressed. But the most important part is the drivers are getting integrated. The drivers are getting intelligent for inverter. They are getting BEST. They are getting functional safety integrated, which is going to make sure that the power stage, which is the core of an inverter, is optimally safe. Finally, one important topic which is slightly different is the very initial inverters, we could hardly see capacitors. Why do we need capacitors was the thought process, right? But over a decade of time, what we realized is this capacitor bank sitting very close to the power switches is very, very critical for the application, right? So many things. You are talking about parasitic inductance. You are talking about currents of 200 amps, right? You need switching currents to be given at an instant. So we need a very bulky bank very close to the switching circuit. How do we do this? That's the challenge, right? So in the vehicles, four-wheelers already there are many technologies adopted which have gone beyond polymer capacitors. But in today in India, most of the good inverters are using polymer capacitors, which is having a better thermal stability. It is having higher capacity density. It is having a very small form factor, right? All these are helping towards a reliable inverter as on today, but we need to develop more. Okay, coming back to the perspective of ROHM, right? We analyze this market for a couple of decades. And where do we want to contribute to this market, right? Is this area, right? We are a semiconductor company. We are pioneers in power devices. We are the first companies which officially released a SiC in the market, right? So we want to contribute to this market by innovating in India for India, right? So we set up a design team very specific to understand the power device need in India and develop a particular die, a new generation of die for this. And how do we take it forward? So we have a list of people as part of this. We have marketing team, we have sales team, we have designers, we have application team who have collated a lot of data to arrive at what we need to do to service this market. We understood the market and we have analyzed what are the key things that needs to be done at the MOSFET level, right? First thing is we definitely need a very high current MOSFET, right? And how do we have a very low thermal performance, having a wide operating junction temperature up to 75 degrees? Then, two important aspects coming from the power dissipation part. How do we go to the lowest RDSN possible without compromising on SOA? That is one idea, right? Then how do we go to a very low switching QG without compromising on the RDSN? These have all been considered, and our design team has been consistently working for the last 1.5 to 2 years to arrive at a part. At the first level, we are looking at coming up with a discrete device, but moving forward, we would like to understand the system intricacies and come up with a module. That is the way forward. Now, ROHM as a company has been involved with SIC for a very long time, and we are one of the pioneers. And we have been working with a couple of OEMs outside India. So what are the benefits that SIC brings into the market, right? So first thing is the low conduction loss, no offset voltage, right? Second thing is very, very low switching losses. Finally, it has a very wide operating range compared to a superjunction MOSFETs. Now, as you see, the switching losses compared to an IGBT with a fast recovery diode or an IGBT with a SPD, full silicon carbide module is having almost 70% reduction of loss. This is the first advantage. What is the benefit it brings at the vehicle level? First thing is we can reduce the battery pack size by 50 kilowatt hour battery to a 46 kilowatt battery. And again, we can not just reduce the battery size without compromising the range, right? We can save the cost. Coming back to other study, like what is the range advantage that we are getting? We did an exercise with our facility to run the WTC test. And as you see, for a city condition with a low profile, right, we are around increasing the range by 10%. Overall, we are increasing by 6%. This is the achievement we can get by the efficient SIC devices. And with regard to torque at the minimum speed, right? Again, as you see here, the efficiency that you are attaining is around 95 compared to 90 with an IGBT device, right? So these are all advantages which are predominant for a high power or a high voltage application, which can be addressed with a silicon carbide. So just to conclude my discussion today, right? So ROHM can support on several solutions for an inverter application. So we have our own superjunction devices, chips, our own silicon carbide devices. We have gate drivers, and we can develop our own module. We can also collaborate with different module makers to come up with a perfect power stage that can address a EV inverter market. That is a goal that we would like to address to the market. So with this, I would like to conclude my discussion today.
One question.
Yeah.
Since you're working with silicon carbide,
Hmm.
do you give a comparative analysis or just a brief look of GaN versus SIC?
Okay, so see, where do you position GaN, where do you position silicon carbide is very important, right? So GaN is very, very good at very high frequency in terms of megahertz at low voltage, right? If you talk about silicon carbide is very, very powerful when you go for a higher voltage, above 600 volt, and typically beyond 200 kilowatts, right? So if you look at GaN will still be very predominant in electric vehicles, but in the DC-DC converters, okay? But silicon carbide, looking at the motors, which probably not run beyond 10 kilowatts, right? But they run at a rails of 800 volt. Silicon carbide will be very strong in the inverter market. That is what I could probably say right now.
May I request Shilpa to come over and give a small memento to Arvind?